Cosmic Enigma. If you're into cosmic mysteries, subscribe. A star can spend millions of years building up to one moment, the final collapse, the shockwave, the light that briefly outshines an entire galaxy. But what if that moment never arrives? In a few nearby galaxies, astronomers have tracked massive stars that looked perfectly normal until they didn't explode. They just dimmed and then disappeared. No bright supernova, no obvious expanding debris, just gone. So what happened? Did the star die in silence, collapsing straight into a black hole? Or are we being fooled by dust, distance, and our own expectations? Tonight's case is about a kind of cosmic death that may be easy to miss. A failed supernova, where a star's core collapses, but the explosion fizzles. If that's real, it changes a basic assumption, because we've been counting supernovae as if every massive star announces its ending. And the universe may not be that loud. To see why this is puzzling, it helps to zoom in briefly on how a typical core collapse supernova is supposed to work. A very massive star burns through fuel in layers until its core becomes mostly iron. Iron doesn't give you energy when you fuse it. So when the core gets too heavy, it loses the fight against gravity. In a fraction of a second, it collapses. Densities spike, and the star releases an enormous burst of neutrinos, ghostly particles that barely interact with anything. That collapse creates a shockwave. In the successful version of the story, neutrinos help re-energize that shock. The shock punches outward. The outer layers get blasted into space, and we see the supernova. But here's the key question. What if the shock stalls? What if the energy isn't enough to lift the star's outer layers? In some models, the core still collapses, but the explosion never becomes a brilliant optical event. Material can fall back in, and instead of a luminous supernova remnant, you can end up with a newborn black hole, formed quietly. So how do you catch something that barely shines? You do it the slow, methodical way. You monitor nearby galaxies for years. You catalog the massive stars you can resolve, and you look for the simplest possible clue. A star that should still be there, that isn't. One of the most talked about case files comes from a galaxy called NGC 6946. Astronomers sometimes nickname it the Fireworks Galaxy, because historically, it's hosted an unusually high number of observed supernovae. If you're searching for stellar endings, it's the kind of neighborhood you'd stake out. In archival images, researchers identified a red supergiant, an enormous, cool, swollen star, exactly the type expected to eventually explode. For years, it was there, a steady point of light at a known position. Then things got strange. The star began to fade. It also seemed to get redder, which can happen if dust forms and blocks visible light. There were signs of a dim outburst, but nothing like a classic supernova. And after that, the star was no longer visible in the way it had been. So, what are the options? Option 1. It's not gone. It's simply hidden. A dusty shroud can swallow optical light and make a star appear to vanish. Massive stars can also vary in brightness, and the farther away you look, the easier it is for normal behavior to masquerade as disappearance. Option 2 is harder to dismiss and harder to prove. The star's core collapsed. The explosion failed. Most of the material fell inward, and what's left is a black hole, with only a faint afterglow, maybe mostly in infrared, if anything at all. Right now, that second option remains an interpretation, not a closed case. The evidence is suggestive. A massive star that dims and is missing without a bright supernova. But suggestive is not the same as confirmed. Still, even a single strong candidate forces an uncomfortable thought. If one massive star can die this quietly, how many have we missed? Let's be careful with the physics, because this is where hype usually sneaks in. A failed supernova doesn't mean nothing happens. It means the outward explosion, the bright, easy-to-spot part, may not fully develop. When the core collapses, it releases gravitational energy. Most of that energy leaves as neutrinos. If the star's envelope is heavy enough, or the shock loses too much energy while trying to plow outward, the shock can stall. Then gravity takes over again. Material falls back. The core can cross the threshold from a neutron star to a black hole, and the visible signature can be small. So what would astronomers actually expect to see? Possibly a brief, faint flash. Possibly an expanding shell that's weak and hard to catch. Possibly a longer-lived infrared glow if dust forms and re-radiates the energy as heat. Or, in the most extreme scenario, almost nothing in light at all. That's why a disappearing star is such an intriguing clue. It's not a dramatic explosion. It's a subtraction. There's also a second channel of evidence that doesn't care about dust. Neutrinos. Neutrinos can escape from deep inside a collapsing star, even if the outer layers don't blow off in a bright display. We have one historic reminder of that. In 1987, a supernova in the Large Magellanic Cloud, SN 1987A, sent a burst of neutrinos that reached detectors on Earth hours before the event peaked in visible light. That doesn't prove failed supernovae exist, but it proves core collapse can announce itself in neutrinos. The catch is scale. Neutrino detections are realistic mainly for collapses in our own galaxy, or very nearby. For the candidates in other galaxies, we're often stuck with light and with absence, which brings us to the practical question. How do you build a census of silent deaths? Long-term monitoring is the method. Wide-field surveys can repeatedly image nearby galaxies. Then, deeper telescopes can follow up in infrared to check whether a missing star is truly gone or just hidden behind dust. The next few years matter here, because the more often we look and the better we see in infrared, the less room there is for ambiguity. And if failed supernovae are common, the implications ripple outward. It changes estimates of how often black holes are born. It affects how much heavy material gets returned to space. And it reshapes the story of what typical stellar death looks like. So the mystery isn't just one vanishing dot. It's whether we've misunderstood the balance between loud endings and quiet ones. Let's recap what we can say and what we can't. We can say that astronomers have identified at least a few serious candidates where a massive star dims and then becomes extremely hard to find without a clear, bright supernova. We can also say the cleanest explanation, direct collapse into a black hole, fits the idea of a failed supernova. But we cannot say it's proven in every case. Dust can hide things. Stars can behave oddly. And even a weak outburst can be tricky to interpret when you're looking across millions of light years. So, what would count as a verdict? Deep infrared observations that still don't recover the star? Late-time imaging that rules out a surviving object? Or the rarest confirmation of all, a neutrino burst from a collapse that never becomes a normal supernova? Until then, the investigation stays open. Because somewhere in the archival data, night after night, galaxy after galaxy, there may be stars that ended. Not with fireworks, but with a quiet drop to zero. And if that's happening, it raises the simplest, most unsettling question. How many black holes were born without anyone noticing? If you want more investigations like this, subscribe for weekly Cosmic Mysteries. If this episode helped, give it a like and share it with someone who loves space, and leave a comment. What observation would convince you it was a failed supernova?